Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be talking about a game called Sotto versus Blotto and mixed Nash Equilibria. My name is Rick and my co-teacher, who originally prepared these notes, is Christoph. So let's start with an outline of what we plan to do today. We'll be talking about this game called Sotto versus Blotto. We'll use it to introduce the concept of mixed strategies and mixed Nash equilibria, which we'll just write as NE from now on. Okay, let's start with Sotto versus Blotto. So I don't know the origins of this game. I don't know where these names came from, but you might want to look it up. There's probably an interesting story behind it. The basic idea is that it's a war game. So there's two competing armies, one controlled by Colonel Blotto, and Blotto holds two valuable cities, and his opponent, Colonel Sotto, wants those cities. Now, for the purpose of this game, let's say we can assign values to these cities, and we will say that City 1 is twice as valuable as City 2. And both Sotto and Blotto see the same thing. They both assign them in the same way. City 1 is twice as valuable as City 2. Now, Sotto is planning an attack and Blotto is planning to defend. The trouble here, the twist, is that each of these colonels commands one indivisible military unit, let's say an army. So that means that Sotto can attack City 1 or City 2, but not both. And likewise, Blotto can defend City 1 or City 2, but not both. Now let's also say that if Sotto and Blotto choose the same city, then Blotto can successfully defend it. So that means that there's no change to the to who owns what or controls what. On the other hand, if they choose different cities, then Blotto loses a city to Sotto. So you can see Sotto is trying to choose a different city than Blotto would choose, and Blotto is trying to choose the same city as Sotto would choose. Blotto wants to defend whichever city Sotto is going to attack. Sotto wants to attack whichever city is not being defended by Blotto. So the question then is, what should Sotto and Blotto do? This is a pretty artificial example, I guess, but it makes for an interesting example to use and introduce some new concepts. So let's explore it. Let's start by looking at the payoff matrix for this scenario. So we have Blotto, who has the option of defending City 1 or defending City 2. And then we have Sotto, who has the option of attacking City 1 or attacking City 2. If they choose the same city, then Blotto successfully defends and there's no change. So nobody gains anything. So that means the diagonal elements are 0 and 0 for both players. Nobody gains, nobody loses. On the other hand, if Blotto defends City 2, but Sotto attacks City 1, which is worth twice as much, as the other city, then maybe we can say that Sotto wins the city and gets, let's say, 10 points, whatever units we're talking about. And Blotto loses that city, so he loses 10 points. On the other hand, if Sotto successfully attacks City 2 and Blotto tries to defend City 1, then Sotto successfully gets the City 2, but that's only worth half as much as City 1. So maybe it's only worth 5 points. And that would mean Blotto would lose 5 points. So here we've got a payoff matrix that represents what we've been talking about. The values 5 and 10 are arbitrary, but they are commonly used in literature, so I'll use them here. You'll notice that this is a zero-sum game. All the elements, 0 plus 0, 10 plus minus 10, 5 plus minus 5, and 0 plus 0, all add up to 0. So the question was, what should Sotto and Blotto do? We have some techniques, some solution concepts that we've investigated already, and let's see how they might apply. We've looked at dominance. So I'll pause the video here, or you should pause the video here, and look for dominant and dominated strategies. Are there any strategies that are dominated by other strategies? And when you're ready, resume the video. Okay, so I hope you saw that there are no dominated strategies. So we can't use dominance to pare this down and reduce it. What about Pareto Optima? Again, you should pause the video here and try to find the Pareto Optima. Okay, if you're back, I'll walk you through it. If we look at this strategy, the question is, can we find any Pareto improvements where nobody would object to switching? We could move over here. Player 1 would be happy with that, but player 2 would object. So that is not a Pareto improvement. Likewise, if we move down here, player 1 would like that, but player 2 would not like that. So that's not a Pareto improvement. And if we compare the diagonal elements, we could switch, but it's not a Pareto improvement. It's kind of borderline. But we could say that the top left outcome is a Pareto optimum because there are no ways to improve. Everybody would agree that there's an improvement. Likewise, we could look at the top right strategy and we would see the same thing. Any movement away from there makes one person worse. So there are no Pareto improvements. If there are no improvements, then it is a Pareto optimum. And likewise for the bottom left strategy and the bottom right strategy. So all of the outcomes are Pareto optima, which again means that it's not really helpful. It doesn't reduce the possible outcomes to let us focus on a smaller solution set. What about Nash Equilibria? Again, you should pause the video and try to find the Nash Equilibria. Okay, welcome back. Let's have a look at them. So I've copied the payoff matrix. Let's use our preference arrows to see if we can find any Nash Equilibria. So if we look at Sotto in the left-hand column, 0 is worse than 5. So Sotto would prefer to attack City 2 if Blotto is defending City 1. That makes sense. And on the other hand, if Blotto is defending City 2 in the right column, then Sotto would prefer to attack City 1. What about for Blotto? Let's say Sotto is attacking City 1, then Blotto would prefer to defend City 1. And if Sotto is attacking City 2, then Blotto would prefer to defend City 2. So a Nash equilibrium occurs when there are no arrows pointing out of an outcome, which means that there's no incentive to move away from that outcome. But we don't see that anywhere here because the arrows form a loop. So every box has an arrow in and an arrow out. So that means that there are no Nash equilibrium found for this game. But here's a weird little thing. Nash actually proved that every finite game, which means you can write it as a finite payoff matrix or hyperdimensional payoff matrix. It has a finite number of players and a finite number of strategies. For every finite game, there is at least one Nash equilibrium. That's a little bit odd, eh? Because that kind of raises the question, so where is the Nash equilibrium in this game? Okay, before we get into that, I should mention that Nash's existence theorem is probably something you want to remember. And I should also mention that Sotto versus Blotto is a term you should remember, what the elements of the game are that we're playing here. So to understand where the Nash equilibrium is, the hidden Nash equilibrium, we have to start talking about something called mixed strategies. So that'll be our next concept. And let me, for contrast, define another term, pure strategies. Pure strategies are the definite choices available to the players. So some examples we've seen in the past, we've talked about up versus down. When talking about the ultimatum game, we talked about the strategies, for example, offer high, also accept all was another one. And in Sotto versus Blotto, some examples are attack city 1 or let's say defend city 2. Those are examples of pure strategies. On the other hand, mixed strategies occur when the action taken is chosen randomly from at least two or more pure strategies. Let's just emphasize that with non-zero probabilities. So, for example, Sotto could flip a coin to decide which city to attack. So the pure strategies available to Sotto are attack city 1 or attack city 2. The mixed strategy could be a probabilistic strategy where there's a chance of attacking city 1 and a chance of attacking city 2. The terms pure strategies and mixed strategies are important and you should remember them. Let's define some variables. Let's let P be the probability that Sotto attacks city 1. And let's let Q be the probability that Blotto defends city 1. So the variables P and Q characterize the mixed strategies for each player. So how does the idea of mixed strategies tie into this idea that we can't find the Nash equilibrium that we were looking for? Well, there's one more step that we need to get to before we can answer that question. We need to talk about expected utilities. So once we've decided that Sotto and Blotto can play these mixed strategies with these probabilities, the challenge becomes understanding what the outcome is going to be in a game. Instead of just having known outcomes, now we have chance thrown into this, and in advance, we can't predict what's going to happen. So the best we can do is get expected outcomes. And I use the term expected from statistics, from probability theory. So what is the utility or payoff of an expected outcome? That is the expected utility. And As I'm sure you've seen in a statistics course, the expected value of something is just the sum of those things weighted by the probabilities of getting those things. Okay. Expected utility will be a term that comes up pretty frequently, so you should get used to it. To make this a little bit clearer, let's throw the probabilities into our payoff matrix so you can see how it all kind of comes together. So I'll draw the payoff matrix again. And let me throw in now the probabilities that we were talking about. Q was the probability that Blotto would defend City 1. So that's the probability of being in the left-hand column here, which means that 1 minus Q is the probability of defending City 2. For Sotto, the probability of attacking City 1 was P, and the probability of attacking City 2 then is 1 minus P. So that's all we need in order to figure out what the expected utilities are for the players. We've got the probabilities of the different choices, and we've got the utilities of the various outcomes. So let's work out what the expected utilities are for each of the players. Let's look at Sotto first. What we're interested in is which choice Sotto should make. Should he attack City 1 or should he attack City 2? So to look at that, let's consider the utility for Sotto if he attacks City 1 or the utility for Sotto if he attacks City 2. If he attacks City 1, that means we're in the top row here, and the utility that Sotto gets out of it will depend on which outcome occurs here. The probability of this outcome is Q, and if that happens, then Sotto gets a payoff of 0. On the other hand, there's a probability 1 minus Q that will end up here. So if we add together these utilities weighted by the probabilities of those occurrences, then we can figure out what the utility for Sotto is to attack City 1, the expected utility. And let's do the same thing considering if Sotto attacks City 2. Again, the probability Q, with probability Q, Sotto will gain 5. And with probability 1 minus Q, there will be no change, so he'll get 0. So the net result is 5Q. So these are the payoffs to Sotto under the two choices he has. Let's go through the same reasoning for Blotto. Maybe you should pause the video right now and try to work this out for yourself. What is the expected utility for Blotto for the two choices Blotto has? And we're back. So the utility for Blotto, if he chooses to defend City 1, well, then with probability P, we're going to be here in this outcome, which means he gets this second number here. So probability P, he gets nothing. And there's a probability 1 minus P that he'll lose a city and lose 5 points. If Blotto chooses to defend City 2, he can expect a utility of P times minus 10 plus 1 minus P times nothing, or minus 10P. So we're very close now to finding our missing Nash equilibrium. The question is now, what probabilities should Sotto and Blotto choose? Well, to help answer that, let's recall our definition of a Nash equilibrium. And that definition is that no player has an incentive to unilaterally change their strategy. That leads us to the definition of a mixed Nash equilibrium, which will be our hidden Nash equilibrium that we couldn't find before. Let's assume, let's call them P star and Q star special values of P and Q, are mixed strategies where neither player has an incentive to switch. And just to expand on that, or reword it, the expected utility for player 1 is always equal or lower if that player chooses another P that's not P star when the other player doesn't change. And the reverse is true as well. If player 1 stays on P star and player 2 tries to move away from Q star, then their expected utility is always equal or lower than it would be at Q star. If that's the case, then P star, Q star is a mixed Nash equilibrium. Mixed Nash equilibrium will be used a lot in the course, so make sure you understand what it is. So how do we use that to actually find the mixed Nash equilibrium? Well, let's think about Sotto's preferences. If the expected utilities for either attack 1, city 1, and attack city 2 are the same, then we can see that Sotto has no preference. He's indifferent to the choice. And indifferent satisfies our criteria because that means he has no incentive to change strategies. So if attacking city 1 and attacking city 2 give the same expected utility, then regardless of the probability P that Sotto has, he can expect the same outcome, the same utility. Sorry, not the same outcome, but effectively the same in that the utility doesn't change. So the odd thing here is that it's actually Blotto that can make that happen. Blotto can enforce Sotto's indifference by choosing Q such that utility of Sotto for attacking city 1 is equal to the utility of Sotto for attacking city 2. So how does he do that? Well, let's just look at those utilities. As you'll recall, they were 10 minus 10Q and 5Q. So Blotto just has to choose a Q that makes that true. And how do we make that true? Well, 10 equals 15Q. We just need Q to be 2/3. So if Blotto chooses Q equals 2/3, then Sotto is going to be indifferent to any choice of P. And the same argument applies to Blotto. He can be made indifferent by Sotto choosing a particular value of P. So the utility for Blotto for his two choices are, let's see, defending city 1. If that's equal to the expected utility of Blotto for defending city 2, then Blotto is indifferent. Has no way to choose between these two options. And those utilities are 5P minus 5, and on the other side, minus 10P. So we see that 15P is equal to 5, or P is equal to 1/3. So, to sum that up, if Sotto and Blotto both choose city 1 with probabilities P equal to 1/3 and Q equal to 2/3, then neither of them has an incentive to switch. And that's just the condition for a Nash equilibrium. So this mixed set of mixed strategies, let's call them P star now and Q star, just to emphasize that these are special values of P and Q, and they are 1/3 and 2/3. That set of strategies defines a new expected outcome in the game, and that set is called the mixed Nash equilibrium. So that's how you can actually find what the mixed Nash equilibrium is. And that highlights or reveals the missing Nash equilibrium that we couldn't find in the beginning. Those kinds of Nash equilibria that we were looking for before, just in terms of these pure strategies, are just called pure Nash equilibrium. And the term pure Nash equilibrium is something you should become familiar with as well. Okay, let's just quickly review what we did today. So we talked about the Sotto versus Blotto game. We introduced the concept here of Nash's existence theorem, which states that there's always a Nash equilibrium in a finite game. And that led us into the idea of discussing pure versus mixed strategies. In order to figure out the value of a mixed strategy, we had to work out the expected utility. And that led us to the idea of a mixed Nash equilibrium, and we compared that with pure Nash equilibrium. Okay, that's all I wanted to talk about for this lecture. Thanks for watching.